From Einstein's special relativity, we know that a system cannot reach the speed of light, but only asymptotically approach c. Here we have length contraction and time dilation as effects related to the velocity. And one important thing is the distinction between the waves that in vacuum continuously propagate at the constant speed we use as reference, and particles making all material systems. Only particles have inertia, therefore matter can only move at speeds lower than waves. Mass is indeed the source of troubles with movements. According to relativity, increasing your speed you increase your inertia, making any further acceleration harder and harder. This cannot be a relative effect. It must be locally true. The system becomes increasingly heavier and its propulsion becomes progressively less effective, making it impossible to reach the speed of light. However, still following Einstein, any observer can consider itself stationary, making the increase of inertia quite wobbly. The speed limit comes indeed from relativity. It is defined by an external observer so that the craft can't reach c from his reference. But each system can consider itself stationary, so from the point of view of the spaceship, it is the other one moving nearly at c. It is therefore impossible to determine which of the two systems is actually moving, and the additional inertia that should explain how the limit emerge is the hot potato game. It's always someone else that can't reach the speed of light the observer is defining. Even more, the observer shouldn't be able to define the limit because physics is local, while we can choose as many arbitrary references as we want, so that even if the spaceship is conserving momentum with uniform velocity, based on the reference, the same craft can be traveling at any speed and possess a different amount of additional inertia. From special relativity, we know all frames measure light at c, regardless for the apparent movement, so that whatever velocity we externally assign to the spaceship, it cannot locally detect neither the alleged additional inertia, nor it can tell how close it is to c. In fact, lacking absolute references, the problem is not the asymptote near the max speed, but how all systems are always stationary here, and no one can be set closer to c than the others, or truly under these effects. The effects are indeed between the systems, and they emerge within observations and interactions. Here is where the relativity lies, and we can use the gamma factor to define effects and limits with respect to the speed of light. But it's not on one of the two, it's what they both symmetrically experience from their point of view. Altogether, we realize that even if matter can't reach the speed of light, the limit and the resulting effects always refer to relativities of interactions and observations, so that it is theoretically possible to have a spacecraft traveling superluminal. The important part is to not violate local physics. In this context, there is a limit for matter that cannot be overcome because it's local, and it's about accelerations. Regardless for the apparent velocity, since particles have inertia, the material system cannot perform accelerations, both negative and positive, that are equal or greater than c squared. These properties allow to discriminate waves from particles. On this side, motion can vary and limits cannot be reached, because if something moves at c, it's no longer a material system, it's a wave. Energy that keeps spreading at constant speed and that we use as reference. A question coming out with superluminal motion regards information and the break of causality. Let's admit we have a spaceship that can outrun light, meaning we have a craft that, while locally it keeps respecting physical laws, it can move faster than light relative to some external observer. We define as initial state some event whose propagation occurs at the fastest possible speed. This propagation can refer to a wave, a state, causality, information, or consequences. It doesn't matter how we call it, it is the constant of reference. Being superluminal doesn't make me know of this propagation until it reaches me. But thanks to my ship, I could both avoid the spreading or get it more than once. In the era of space-time, everyone is always on its own present, and it doesn't matter what can happen. Physics only care about what is actually occurred. This means that I cannot change something that has already happened, and speed has nothing to do with traveling back and forth in time. Space-time is always cumulative in the same directions for everybody, regardless for the movements. With superluminal capabilities, however, I could carry some information faster than light or anticipate some future event. It doesn't break causality because physics is always in the present, and whatever the speed, the craft still occupies always and only one locality at a time. Past cannot be changed, and the future is not written until it becomes the reality of the present. The universe doesn't care about your movements if you don't locally break continuity and conservations. This way, information can be conveyed faster than light, but this is achieved by the action of a life form. It's not spontaneous physics. On one side there is consistency and predictability. This energy cannot physically spread faster than c. But on the other, there are life forms capable of actions that physics can't. Thanks to their minds, humans can, as example, exploit electricity and fly tons of metal, bending the laws of physics in its favor. So there must be some intelligence that built the superluminal craft to outrun the propagation of the wave. For this to be achievable, the spacecraft must have its own space-time, and it probably makes inevitable the manipulation of gravitational fields. Here light will still be measured at c according to special relativity, but spaceship can move with relative speed greater than c of another space-time. Something similar can be witnessed with superluminal knowledge. With entanglement as example, we have two observers very far apart, and we send each one a particle or a wave from the couple we initially prepared. Looking at what they received, both observers can also determine what the other has wherever he is, because the life forms know both the common source of the particles and where the two systems are sent. So entanglement is a physical correlation humans exploit to get additional informations. Superluminal is not just about movements, it's also about observations. Two faraway galaxies can have such a high relative velocity that light emitted cannot reach the other system, and the two are unable to see each other. But two spacetime can also be far away because of gravity. In this fashion, a black hole can be considered superluminal with respect to everything else outside. His gravitational well is so strong to achieve an effect similar to faster-than-light motion, because light cannot go directly from one spacetime to the other. Causes and dynamics are different, but with both scenarios, systems are separated by a superluminal distance, and an event horizon emerges. In closing, the two limits discern particles with inertia from waves freely propagating at constant speed. But while one constraint involves relativity, the other is local. Achieve superluminal motion is far from trivial and requires to modify the surrounding space-time. However, if continuity and conservation are respected, there are no issues with causality because you still occupy just one locality. After almost 50 years, the Voyager 1 has barely reached the boundaries of the solar system, traveling about 17 kilometers each second, which sounds a lot, but is not. So humans must go way beyond Newtonian propulsion if they want to explore the immensity of the universe. Milky Way spans 90,000 light years, and light takes 2.5 million years just to reach our closest neighbor Andromeda. The two are part of the local group, counting more than 100 galaxies over 16 million light years. Superluminal motion is thus inevitable because space is so wide that, even considering time dilation, traveling at the speed of light is still too slow for human lifetime.